Hello everyone. I'm sure all of you are doing well. In the last class, we had done one colligative property, what is called relative lowering in vapor pressure. I'm sure you have understood what is meaning of relative lowering in vapor pressure and what is meaning of colligative properties. And you have to do different types of numericals based on those formulas. Once more, what is meaning of colligative properties? Colligative properties means when we add some solute, the change in vapor pressure or boiling point or freezing point will not depend on which solute we have added. It will depend on the amount of solute or number of particles of solute. So that's meaning of colligative property. Another colligative property we have to do is elevation in boiling point. Now, before we go for this elevation in boiling point, now how do we define boiling point? Usually in lower classes we say the temperature at which a liquid will boil at a particular pressure is called boiling point. Now when a liquid boils, suppose if you take pure water in this container and we have covered it with a lid and we are heating it. Now what will happen? Due to increase in temperature, its vapor pressure will increase. Okay, and a time will come when these two pressures will be in equilibrium. And at this pressure, when this external pressure, that is pressure acting on the surface of the liquid, becomes equal to the pressure by which the vapor is passing, the liquid is passing into vapor phase, these two pressures become equal, then the liquid will boil. So when a liquid will boil, the liquid will boil only when its vapor pressure becomes equal to the external pressure. Now if the container is open, then in that case external pressure will be atmospheric pressure. So pure water will boil when its vapor pressure becomes equal to the atmospheric pressure. Now we say that pure water boils at 100 degrees Celsius. There is no meaning of it. We have to say that pure water boils at 100 degrees Celsius at 1 atmospheric pressure, that is 760 mm of H. What does it mean is that at 100 degrees Celsius the vapor pressure of water becomes equal to the atmospheric pressure. It means vapor pressure of water at 100 degrees Celsius becomes equal to 1 atm, and then only it will start boiling. Okay, so that's meaning of boiling point in terms of vapor pressure. So boiling point of a liquid is the temperature at which its vapor pressure becomes equal to the atmospheric pressure. Now, what is meaning of elevation in boiling point? Pure water boils at 100 degrees Celsius. But suppose if we take drinking water, sea water, or water in which some solute, non-volatile solute is added, then it will not boil at 100 degrees Celsius. It will boil above 100 degrees Celsius. So if some solute is present in a liquid, then its boiling point will increase. This increase in boiling point due to dissolved solutes, non-volatile solute in a liquid, is called elevation in boiling point. Now why it happens? Graphically we can understand. We know the boiling point of water is 100 degrees Celsius at 1 atmospheric pressure. Now if we plot taking vapor pressure curve. Say in this direction we take vapor pressure and here we take temperature. We have seen that and say pressure is here 760 mm of Hg. And say we have a liquid at this temperature, say 25 degrees Celsius. So definitely at 25 degrees Celsius, its vapor pressure is much lower than 760, so it will not boil. So what we do, when we increase its temperature, its vapor pressure will increase. Once its vapor pressure becomes equal to the atmospheric pressure, this liquid will start boiling. Suppose we call it as TB naught. So here TB naught is what? TB naught is boiling point of pure liquid. And this is vapor pressure of pure liquid, that is vapor pressure curve of pure solvent. Okay. Now suppose if we add some amount of solute, non-volatile solute to it, we have seen the vapor pressure curve of the solution will be below it. It will be like this. This is for solution. So again, this solution will also boil only when its vapor pressure becomes equal to 760, that is 1 atmospheric pressure. Now what you find from here, this graph is at TB0, the vapor pressure of solution, this vapor pressure of solution is below 760. So definitely it will not boil at this temperature. So what we have to do, we have to heat it further. So if we heat it further, see here at this point, its vapor pressure of this solution at this temperature, say let it call it as TBS. So what you find here is for solution, the vapor pressure becomes 760 mm of Hg at this temperature, which is much higher than the boiling point of pure solvent. So boiling point of solution here, TBS stands for boiling point of solution, is higher than the boiling point of the pure solvent. Not stands for pure solvent. So and this difference that is delta TB, this delta TB is equal to TBS minus TB naught, and this is elevation in boiling point. Okay, and see here, this elevation in boiling point is directly related with the lowering in vapor pressure. If this is vapor pressure of pure solvent, this is vapor pressure of solution, then this difference is delta P, that is lowering in vapor pressure. So elevation in boiling point is related to the lowering in vapor pressure. So from here we can write delta TB is proportional to delta P. So if there is more lowering in vapor pressure, there will be more increase in the boiling point. And this lowering in vapor pressure, we have seen already, will depend on the mole fraction of solute. Mole fraction of solute, and this mole fraction of solute will be directly proportional to molality of the solution. Okay, and so from here we can say that elevation in boiling point is directly proportional to mole fraction, and mole fraction does not depend on the nature of solid, whether you have added urea or glucose. It will not depend on that. It will depend on how much urea or how much glucose is added. So from here we can say that elevation in boiling point is also a colligative property. So from here we can write delta TB is equal to say proportional to strength in molality. SM stands for strength in molality. Therefore, delta TB will be equal to some constant KB into strength in molality. Okay. Now, delta TB is equal to KB into strength in molality, where KB is constant for a solvent, means each solvent will have a specific value of KB. And now what is KB? KB is called ebullioscopic constant, also called molar elevation constant. Now what does it mean? See, if molality of the solution is 1 m. Now what is meaning of 1 m? It means in 1 kg of water 1 mole of non-volatile solute is added. Suppose we have taken 1000 gram of water and in that we have added 60 gram of urea. Okay, so this is meaning of molality is 1. Then in that case delta TB will be equal to KB into 1 is equal to KB. So here molar elevation constant or ebullioscopic constant means increase in boiling point when molality of the solution is 1 for a unimolar solution. For example, KB for water is approximately 0.52 Kelvin kg per mole. Now what does it mean? It means if we take 1 kg of water and in that we have added 1 mole of urea or 1 mole of glucose or 1 mole of fructose, then the boiling point will increase by 0.52. It means if we have 1 kg of water, we have added say 180 gram of glucose. 180 gram of glucose means 1 mole of glucose. Then that solution will boil at 100.52 degrees Celsius. Okay, you should not confuse here with one thing, that it is delta TB is not boiling point. It is elevation in boiling point. Boiling point is not a colligative property. Elevation in boiling point is a colligative property. So if we, instead of glucose, if we take 60 gram of urea in 1 kg of water, in 1000 gram of water, again the boiling point will increase by 0.52 degrees Celsius or by 0.52 Kelvin. In SI unit it is 0.52 Kelvin kg per mole. Even if you take in degrees Celsius, it will be 0.52 degree kg per mole. Why? Because this is not the temperature. This is the difference of the two temperature. If you take the temperature boiling point in Kelvin for the solution and the pure solvent, when you take the difference, 273 will cancel, and so the difference will remain again 0.52 only. Okay, now how we use this method to determine the molecular mass of the solute, provided the solute is non-volatile, non-electrolyte. determination of molecular mass by ebullioscopic method. Okay, so we have derived this formula delta TB was equal to Kb into strength in molality. Now if like that day I had given you a small W is the mass of the solute, small m is molecular mass of the solute, capital W is the mass of the solvent, and capital M is the molecular mass of the solvent. Then molality will be W into 1000 divided by, keep in mind this 1000 will be only when this W we are taking in gram. If we are taking in kg, then this 1000 will not be there. M divided by capital W, delta T. So this is the formula we get for elevation in boiling point. Kb is ebullioscopic constant. I said it is constant for each solvent. For example, for water it is 0.519 approximately. We take it as 0.52. 1000. Okay, m is molecular mass of the unknown solute. We don't know what its molecular mass. Capital W is the mass of the solvent, say water, that we will know. So if we can measure this delta TB, that is difference in boiling point, then molecular mass M can be calculated. But problem is this difference in boiling point, elevation in boiling point, it's so small, it is so small that it is not easy to measure with ordinary thermometer. In ordinary clinical thermometer, we have 1 degree, we have divided into 10 parts, isn't it? 10 divisions are there. So we take more sensitive, highly sensitive thermometer where 1 degree is divided into 50 parts or 100 parts. So when we have to go for molecular mass determination, for that we have to measure the elevation in boiling point, and to measure the elevation in boiling point we have to use very sensitive thermometer. One of them is what is called Beckmann's thermometer. We use Beckmann's thermometer. Okay. At the same time, we have other limitations also when we go for this method. So limitations of ebullioscopic method. First of all, the solution should be dilute. This condition I had given earlier also in lowering in vapor pressure. Now, why the solution should be dilute? Always we say that solution should be dilute. It is assumed here whenever we are deriving this formula that there is no interaction between solute molecules when we have added to the solvent. Means each solid molecule is free. But if the solution is not dilute, if it is concentrated, the solid particles are very close to one another and there will be some interaction. There will be interaction between solid and solvent molecule also. So solution should be dilute. Second, solute should be non-volatile and non-electrolytic. Non-volatile and non-electrolytic. Means we cannot take sodium chloride in this case, because when we add sodium chloride, we will think that suppose we have added 10 molecules of sodium chloride. If we add 10 molecules of sodium chloride, it will break into 10 ions of sodium and 10 ions of chloride. So we will expect the elevation in boiling point due to 10 molecules, but actually the elevation in boiling point will be almost double to that expected value, because that once we add the molecule inside water, it will dissociate to give sodium ion and chloride ion. Okay, and since it is colligative property, it will not depend whether it is NaCl or Na plus or Cl minus. It will depend on how many particles are there. Third, in some cases what happens when you add molecules, solute molecules inside the solvent, they associate together. For example, if you take 10 molecules of benzoic acid, dissolve in benzene, benzoic acid molecules will associate, they will dimerize, and inside you will have only 5 molecules. So elevation in boiling point will be almost half of the expected value. So solute should not undergo association also. Should not undergo and last we have to use very sensitive thermometer. Okay, so these are conditions, or we can say these are the limitations for molecular mass determination by ebullioscopic method or elevation in boiling point method. Now what I said you is Kb is constant for a solvent. Different solvent will have different value of Kb. For benzene, if I remember, it is about 2.6. For water it is 0.52. Now how we determine the value of Kb for a particular solvent? Thermodynamically we can calculate it. Thermodynamically, Kb is given by RTB naught square divided by thousand LV, where R is gas constant, you know that. Tb is boiling point of the pure solvent in Kelvin unit. LV is latent heat of vaporization. Latent heat of vaporization per gram. If we take per mole, for 1 mole, then it will be RTB naught square divided by 1000 delta HV into M. Here again, this M is molecular mass of the solvent, I've given you already earlier, and this will become now latent heat of vaporization per mole. Okay, so this is how we find out the value of Kb. So what you have to do is, I have uploaded the note of this part also. You solve the different type of question answers given in the book. If you don't have book, I have uploaded already in the first video the small note with different type of question answer in that. Okay, thank you very much.